Today, I'm going to give an introduction to heterostructured materials. My name is Zhu Yuntian. I'm in the Department of Materials Science and Engineering, the Mechanical Behavior Division of Shenyang National Lab, City University of Hong Kong. In nature, there are plenty of heterostructures developed in the over millions of years. In essence, heterostructures can be regarded as non-uniform structure. One example is heterostructured bamboo. You can see this is the regular bamboo. If you cut the cross section, you can see the fiber distribution is non-uniform. So the fiber in the software matrix as heterostructure, and the distribution is also in a gradient, has a gradient. So this is this is a two-level heterostructure. This heterostructure makes bamboos very strong and tough. In Hong Kong, they use the bamboo as scaffolding for repairing buildings because they are strong, tough, and lightweight. Another heterostructure example is seashell and the bones. For the seashell, you can see that if you cut open the seashell, you get different layers. Each layer, in this calcite layer, nano-nacreous layer, you can see it has many bricks. This is like a brick and a mortar composites. Each brick is like a really calcium brittle plate. In between is an organic matrix. And now also, if you look at each brick inside, again, is another level of heterostructure that has nanocrystallized with organic matrix. And we collect the bone, it's the same. You see on the surface, you have very high density. And as you go away from the surface, you can see you have more and more porosity, which make the bone a gradient structure. Why there's a heterostructure in nature? These heterostructures are evolved for millions of years, and they are very strong and tough to survive the harsh environment, such as a storm, enemy attack, etc. This will make the plants and animals in nature survive better. And in addition, it sustains the highest, such heterostructure can sustain the highest load at a minimum material cost. When you use least material, give you better performance. Again, that helps the animal to survive, animal and the plants to survive. There are also man-made heterostructures. The simplest is this like a mud in a straw heterostructure. It's a type of composites. This has been used for like over 5,000 years by our ancestors. And this has been extensively used like to make a mud house. And this is in some part of the world, they are still building houses with this type of material. In ancient China, they use this to make the Great Wall. Some of the Great Wall made this way. And if you go to US, go to New Mexico, There's a famous city for tourism. It's called Taos in northern New Mexico. They have this kind of typical adobe house. This is actually made of mud and straw, but now they are making, of course, concrete and fibers. Another type of man-made heterostructure is the swords and the weapons. Okay, this is a micrograph of with a layered structure of a Chinese Han Dynasty sword made in AD 77. And here's another one, is a 13th century Persian Fort Damascus steel sword. You can see it also has a layered structure. In modern time, they are still making this type of sword. See, this one is a Japanese samurai sword. You can see this is made of a layered structure. The reason they have this structure is to make the sword strong, tough, and sharp. Of course, if you go to advanced engineering materials, like this Boeing 787 Dreamliner, and this Dreamliner can save the fuel cost by 20% to give make it competitive. The reason for that is 50% of the structure is made of composites, carbon fiber composites, which make them lightweight and strong. Okay, so all these materials are heterostructures because they are not uniform. However, here for the heterostructured materials, we want to narrow the scope a little bit, actually a lot. Here's how we define heterostructured materials here. They should have large mechanical or physical property difference among different zones, large than 100%. Why 100%? Because it sounds like a good number. Just like a nanomaterials, they use a definition of 100 nanometers as the limit, because it's easy to remember. Secondly, these heterostructured materials need to have significant synergistic effect. I call that 1 + 1 larger than 2. What I mean here is not all non-uniform structure will give you benefits. Only you design the heterostructure in a certain way, in a microscopic way, so that you can get this advantage over conventional homogeneous material. So it has to have a synergistic effect. Okay. Then you may ask, what causes this synergistic effect? This is caused by interzone coupling or interaction. Okay. So which means you have to design the zone very well so that you have a very high interzone coupling and interaction. What's the real mechanism for this coupling and the interaction? For structural materials, this is via geometrically necessary dislocations. We call that GNDs. These GNDs also produce strain gradient. We will elaborate more on that later. For functional materials, this coupling and interaction is via physical mechanisms, such as magnetic coupling for magnetic materials, magnetic heterostructured materials. I'd like to stress that this definition was by a group of scientists scientists all over the world, like actually 14 of them, in a paper published in Materials Research Letters in 2021. We realized that for a new field, for a new type of material, no matter how you define it, there's always people who have a different opinion. But here, at least we reached a consensus among scientists over many countries. The focus of this tutorial is on structural heterostructured materials. And the definition, of course, let's repeat it again. It has a large strength difference among different zones, larger than 100%. And all zones can deform, typically, all zones can deform plastically. So this differentiates them from conventional composite materials. For example, for composite metal matrix or polymer matrix composites, the reinforcements are usually brittle, high strength but brittle. The second one is each zone can be polycrystalline or single crystalline. And I'll show you that later, show more of those. Of course, it needs to have significant synergistic effect, 1 + 1 rather than 2. I'll show you that effect later also. According to this definition, we have all these type of few type of materials which have been reported in the literature, like a heterogeneous lamellar structure, this one, gradient structure, this cartoon, harmonic structure, this one, bimodal structure, and multi-phase structure. And all these structures, if you look at their structure, they are so different. Then how can you put them, classify them together? This is because their superior mechanical property are all based on one fundamental basis. That means coupling via GNDs or interaction via GNDs. This produce strengthening and or hardening, which is induced by hetero deformation induced stress. Okay, we call that HDS stress. I'll show you more this topic, this concept later. Okay, with this definition, I'd like to introduce several types of heterostructures already reported in the literature. The first one is a heterostructured lamellar structure. And this is the cartoon. In this cartoon, you can see this large grain lamella, which is soft. They are embedded in the nanostructured or finer grained matrix. Okay, each lamella can be approximated by this ellipsoid with the axis of A, which is longest axis, B, and C. Okay, so this can be typically produced by cold rolling by partial recrystallization, in which case you get A is very large, B is in the medium, C is very small. It becomes a lamellar structure. Okay, it's a polycrystalline lamella. However, if B and C are same, they are much smaller than A, and this lamellar structure will become a heterostructured fibrous structure, okay, called HFS. And that can be produced by cold extrusion, drawing, then plus partial recrystallization. The second type of heterostructure is called the bimodal structure. I think many people are familiar with this. There are extensive publication on this. I'd like to stress that this is not the most effective heterostructure. This can be typically produced by annealing ultrafine grain metals to have if it has abnormal grain growth, some grains grow larger like this. Of course, for bimodal structure, you can also have a trimodal structure in some cases. Of course, another way to produce this type of structure is by powder metallurgy. Gradient structure has also been extensively reported. There are two types of samples with gradient structure. One is a gradient plate like this. Okay, if you get a nanostructured surface, and in the center you got a coarse-grained center, and if you look at the grain size distribution, here's the cartoon. Another type of sample is a rod shape, like this rod sample. The surface is nanostructured. If you go across the cross section from the surface to the middle, you also see a similar thing. And we look at the grain size, typically from like about 100 nanometer or even smaller to many micrometers. Okay, this is the gradient structure. This is one type of heterostructure. The third type of heterostructure is called a dual phase structure. Of course, you can also have a multi-phase structure. This can be typically produced by thermal treatment. Like actually in the steel industry, there are a lot of dual phase structures, although we did not pay attention to them, never called them dual phase structure. Like a pearlite, the type of heterostructure, dual phase structure. Depending on this phase content, you can have a different type of dual phase structure. In this one, with the soft is the yellow phase is softer, and you have this hard phase embedded in the softer matrix. In conventional industry for steels, they typically are this type, which means hard phase embedded in softer phase. On the opposite way, if we go here, you have this softer phase embedded in the hard matrix. Actually, this is not very common in the industry, but this is the most effective heterostructure, dual phase heterostructure. Of course, when the two phase has a similar volume fraction, you may form this kind of structure. This can be formed by eutectic or eutectoid phase transformation. And there you can, of course, in the matrix, you can also precipitate out the second phase again, and it can become like a multi-phase heterostructure. Okay. Harmonic structure. So this is invented by Professor Kei Amiyama in Japan. And basically, you can see this is called harmonic structure. It's also can be regarded as a core shell structure. It's typically produced by powder metallurgy. If you have more interest, you can check out Professor Kei Amiyama's work to have more information. Basically, each of these are from a big powder, and he did like low energy ball milling to make the surface of the powder nanocrystalline, while the inside of powder is still coarse-grained, and consolidated them together, you form this structure. Layered structure. This is already also very common. In this example, it's a layer of bronze, is yellow bronze, and a layer of copper is red one color, is pure copper. Okay, this is produced by accumulative rule bonding. It gives you this layered structure. Okay, each layer are continuous. For metallic materials, we are all familiar with this banana curve. What this means is we have the strength and the ductility trade-off. And if you want to have high ductility, the strength will be lower. If you want a high strength, the ductility will be lower. However, we want both. We want both. But this, if you look at our textbook, and this is not possible. And if you tell people you want this, like what I did once at a conference, people will laugh at you. I think you are like, what are you talking about? Okay, now the question is, how do we, as an engineer, we want the material we make both strong and tough like this, okay? That's all we want to do. And then how do you make a metal or alloy strong? This is simple. If you look at our textbook, there are several ways. One way to make is solution hardening. You add you add alloy element, make a solid solution hardening. Then you can have precipitation hardening. It's also called second phase hardening, and this is very important for like aluminum and magnesium alloy. That's the primary way for them to make high strength, improve their strength. Or you can use a grain refinement. In the past like 40 years, and people are working on nanostructured metals. Basically, the principle for that is the whole patch effect. Like the grain size is smaller, the strength become higher. That's for grain refinement. Basically, you're using the whole patch effect. Then cold working, if you deform them at room temperature or liquid nitrogen temperature, it will become stronger. That's because you increase the dislocating density. That's called dislocating hardening. For this is Taylor's equation. The rule is the dislocating density. Higher dislocating density give you higher strength. Okay, this can make the material stronger. However, high strength alone is not good enough. Ductility is also needed for real application, because without ductility, it's not safe to use the material. Then how do you make metals ductile? It turned out not to be not so simple. Okay, first we have to define that what's ductility. I need to stress again that ductility is measured under tension. We often have people asking, how do you measure ductility under compression or under other deformation mode? No, you cannot measure ductility using any other tests except under tension by definition. Okay? When you measure them under tension, there's always a strength ductility trade-off. This is because under tension, the sample will become unstable. We call that a necking before it fails. Okay, how do you judge whether the sample will fail or not? This is by first, there's a hard criterion. So in this equation, you can see d sigma, d epsilon, normalized by the flow stress plus m larger than 1 for stable tensile deformation. This m is the strain rate sensitivity. Okay, this is especially important for deformation at high temperatures. High temperatures when m is relatively large. Like for silver plastic deformation, m is larger than 0.3. Okay, however, at room temperature, m is typically very small, equal to 0.0 something. Okay, as a result, this is since this is much smaller than 1, where you ignore m, now this hard criterion become a considerate criterion. That means d sigma, d epsilon, which is the slope of the tensile stress strain curve. It has to be larger than the flow stress. By the way, here all the stress and strain are true stress, true strain. Okay. This turned out to be the problem which caused this banana curve. One example is this. See, this is nanostructured titanium. Okay. So under compression, let's look at the compressive curve. Under compression, coarse-grained titanium, you see the stress continue to increase. You have a very good strain hardening, and which is the slope of the curve. However, for nanostructured titanium, you see the flow stress is much higher than coarse-grained titanium, which means the sigma is much higher. But if we look at the slope, the sigma, the epsilon, is close to 0. And this becomes 0, this becomes high, of course, it's not stable. So not surprisingly, if you test this titanium under tensile stress, you see it goes up under slow deformation. It started necking. The highest point is for the highest point, that's the necking point. Then this is all the necking strain. So necking strain does not count here because its length is sample dependent, sample geometry dependent, geometry and set dependent. Okay. So metals and alloys have been studied for over a century. Now the question is, do we still have new unexplored mechanisms to improve the strength and ductility? In other words, is it possible to have any new breakthroughs? So with that question, I'd like to introduce a new paradigm materials design and its theoretical basis. Basically, this new type of material is called heterostructured materials. And heterostructured means they are non-uniform. However, I'd like to stress that it's just not non-uniform in any way you want. It has to be non-uniform in a certain way to give you this benefit. The heterostructured materials have been found to be able to simultaneously increase the strength and work hardening rate by heterodeformation induced hardening. We call that HDR hardening. This used to be called backstress hardening. I will show you later. Backstress hardening, this concept is not accurate. It's wrong in most cases. If you compare with conventional material, conventional strengthening is usually the strengthening mechanism we discussed earlier often decrease the strength hardening rate, which is why they give you lead to the well-known banana curve. Okay, now you may ask, how is HBI stress produced? As you look at this cartoon, this is actually not very difficult. And here there's a fracture rate dislocation source. Okay, it emits a lot of dislocations to slip on the same plane. They all get stopped by the zone boundary. See, here's the red is the softer zone, the red is the harder zone. In between this red line is the zone boundary. Okay, the fracture rate source is in the softer zone. Okay, since these dislocations are from the same fracture rate source, they have the same Borges vector. If they have the same Borges vector, they pile up like this. This will produce a long-range internal stress to prevent, to block any further dislocation to slip forward. Basically, can stop the fracture rate source to emit new dislocations because these dislocations repel each other. So if you calculate the stress the dislocation has along this line, how that repel the follow-up dislocations, and the stress profile will be like this. Follow this yellow line. This is called back stress, because your applied stress will drive dislocation forward. Your back stress will drive the dislocation backward, which means that's why it's called back stress, because it's opposite to the applied stress. Okay. So the back stress will cancel your applied stress, so that although your applied stress is enough to activate the flange radius source, but after the development of back stress will like neutralize or cancel some of the applied stresses, so that the flange radius source will stop emit new dislocations. Okay, this is the back stress. If we look at our textbook, at the interface zone boundary, okay, there's a stress concentration of N tau A. Tau A is applied stress, okay? N is the number of dislocations piling up on this stable plane. So the stress concentration is N tau A. That's the force on this at this point. The N tau A that much at this point. Okay. Then any force needs to be balanced. Okay. So because of this stress concentration in the hard zone side, there must have a forward stress to balance this back stress. So if you look at the forward stress, is the direction opposite to back stress. It's the same as the applied stress in its direction. That's why it's called the forward stress. And at the boundary is opposite, the direction opposite to back stress, but the magnitude is the same. But if you look at how they decay away from the boundary, the back stress will decay faster than the back stress, which is why although at the boundary they cancel each other, but overall they cannot cancel each other because they decay in different way. And together they produce HDI stress. Okay, HDI stress is a result of interaction between back stress and the forward stress. When you measure it using mechanical testing, what you measure is their collective reaction. It's not a back stress. You cannot measure back stress using mechanical testing because they are a couple. Okay, this is why back stress concept used in the literature are mostly wrong. I'm not saying back stress does not exist. It still exists in the soft zone. Only problem is you cannot measure it using mechanical testing. If you want to measure this, you may need to use like a neutron diffraction or X-ray diffraction if you only measure the soft zone part. Okay. With the back stress, it comes with, it also gives you strain gradient because each dislocation, the plastic strain is caused by the slip of dislocation, which means at the dislocation source, you have the highest plastic strain. At the interface, so this dislocation has not reached the interface, like I stopped here, the strain is 0. At the interface, it is equal to this many Box vectors. Here it's like 7. So if you plot this strain for this type of flange radius source, so strain is 0 at the interface, it becomes very high at the flange radius source. So this is a strain distribution. The derivative of this profile is a strain gradient. Is a strain gradient. Okay. The strain gradient, we call that the sigma dx. You can see the d epsilon dx. You can see this d epsilon dx is positive, above 0, because the strain increases with x. So this is positive. So that's why we call this as a positive strain gradient. Okay, let me repeat. The strain gradient caused by GND pile up from a Frank-Ridge source in the soft zone is positive. It causes positive strain gradient. On the other hand, if the dislocation source is on the zone boundary, and it will be opposite. The Pareto strain higher side of the zone boundary, it become smaller, smaller, approaches zero, far away from the zone boundary. So if you the derivative of that, which is the strain gradient, that will be negative. So if the dislocation source is at the zone boundary, then the strain gradient will be negative. Okay, let me repeat. If the Frank-Ridge source is in the soft zone, it produces a positive strain gradient. If the dislocation source is on the zone boundary, it will produce a negative strain gradient. Okay, here's how this GNDs can rearrange them. Okay, GND structure. How can they rearrange them? The first type, you know, of course, if all the GNDs pile up along a sliver plane, these produce a long-range internal stress, which is the back stress, and back stress then it will collectively will induce a forward stress, and then forward stress and the back stress collectively produce HDI stress. However, if all these GNDs with the same box vector, they pile up like this on top of each other. I assume everybody knows what this is. This is a small angle grain boundary. So it will produce lattice rotation. However, there's no long range internal stress because in the long range, there is stress field that cancel each other. So this does not produce any HDI hardening. The third type is the mixed type. So this produces a medium HDI hardening. Another scenario is all the dislocations, they are random. Okay, the box vector is in all different ways. They're totally random like this. This type of dislocations are called statistically stored dislocations. They produce no back stress because they do not produce long range internal stress. Okay. No back stress, no HDI stress here. Conventionally, in conventional materials, you know, the grain sets are not uniform either. They will produce some HDI stress because not totally uniform. However, their HDI stress is mostly ignored because we are so small. So, for example, the dislocation strengthening using the Taylor's equation. See this Taylor's equation, and this is rho S is the density of statistical dislocation. Rho G is the density of geometric GNDs. Okay, density of GNDs. So it does not differentiate statistical dislocation or GNDs. They're all the same. So in this equation, the HDI stress is simply ignored because they are kind of low. So, and then the work hardening, you can see use that equation. You can see work hardening caused by what? By the total dislocation density increase, which means the work hardening caused by dislocation accumulation. So we call that dislocation hardening. Oh, by the way, the work hardening here is not caused by total dislocation density. It's by dislocation density increase. which means if you have very high total dislocation density in the beginning, later you do not decrease at all, then this does not change. The work hardening will be 0. Okay. So that's now we have defined what's ideal strengthening, what's ideal hardening. Okay, ideal strengthening is the ideal stress at the yielding point. Okay, if you measure the ideal stress at the yielding point, that causes ideal strengthening because that increases the yielding strength, the yield strength. Okay, then if ideal stress continue to increase with a further tensile strain, then you have ideal hardening. Let's call it ideal strain hardening. Okay, the ideal stress continue to increase with applied strain. Give you ideal strain hardening. It will help to retain or even increase ductility. As a result, it may produce a combination of strength and ductility that is not possible, not accessible to conventional homogeneous materials. This is another cartoon to show you how the ideal stress works. In conventional material, we are using the dislocation strengthening and dislocation hardening to improve the strength and ductility. It's more like this rock above the sea level. And in heterostructured materials, on top of that, in addition, on top of that, we have ideal strengthening and ideal work hardening to further improve property. So if you have a very good property for conventional material, conventional metal and alloy, and if you make them in the heterostructure, we can make your material even better. Okay, remember I showed you this. We all want is both high strength and high ductility. I talked about this at a conference. They laughed at me, and then I'm going to show you this can be done. So this is an example. The heterostructured lamellar titanium. They studied with coarse grain titanium with an average grain size about 44 micrometers. Then using a symmetric ruling, we produce ultra fine grain, and then we did partial recrystallization. Actually, this work is done by Professor Xiaolei Wu, and like 25% by volume of the sample get recrystallized to form these larger grains. This TM give you the example of recrystallized lamellar like this one with average grain size about 4 micrometers. It's surrounded by the ultrafine grained matrix. You cannot see the grain size here because they are so small. The recrystallized grains, they are very clean, dislocation free. So by this, we can say that the grain size increase or average grain size increased and also dislocation density also decreased. Here is the mechanical property. Okay, here's the coarse grain titanium, the same batch of material. It has typically relatively good ductility. This is uniform elongation, about 80%. However, the yield strength is only like 300 megapascal. When we process them into ultrafine grains, so this ultrafine grain titanium, the strength is about 900 megapascal, but the ductility decreased to about 2%, which make it useless. Is ductility not high enough for real application. Then you look at the heterostructured titanium. Here, look at these 2 data points. The strength is similar to ultrafine grain titanium. Look at the ductility is even higher than coarse grain titanium. So what's happening here? that totally defies this banana curve. And I'd like to point out a few problems with this data. First, by partial recrystallization, the sulfur lamella zones, their grain size is bigger, like 4 micrometer. So the average grain size has increased, but the yield strength does not decrease. So this violates the whole patch relationship. Okay, this the wild-knowing whole patch relationship does not work anymore. Okay, then and also during the partial recrystallization, the dislocating density, total dislocating density, has also decreased because the recrystallization and the recovery. But the strength does not come down, and this is violate the well-known Taylor's equation. So this does not work anymore. Then we look at the strain hardening rate. Strain hardening rate, this black line is the strain hardening rate of coarse grained titanium. This green line is the strain hardening rate of ultra-fine grained titanium. When you look at the heterostructured titanium, it's higher than both of them. It totally violated the rule of mixtures. So this violates every principle we have learned from our textbook and from the literature. So what's going on is this is all caused by this HDI strengthening, HDI work hardening. What I'm saying is that heterostructured materials have a superior property because of a totally new science we are not aware of, we have not explored before. So that's good news and give us a new science to study. And then you may ask, okay, what's really going on for this material? Because this superior property, why did it violate these principles? First, you look at this grain. This is a 4 micrometer recrystallized titanium grain. In this grain, you look carefully, look at this dislocation pile-ups. Those are all the GNDs. We got many of them, in different directions, actually. Okay, this large GND with large grains, it has a lower strength, like let's say 400 megapascal. We do not know, but let's assume it's 400 megapascal. And when you during the tensile testing, when you apply the stress is above 400 megapascal, and this is dislocation source will start and emit all these GNDs. You see the GNDs, okay? The GNDs will go toward the zone boundary and get stopped here. It cannot get across the boundary because this grain, softer grain, is surrounded by hard matrix. The matrix needed a stress of 900 megapascal to deform. So they got all stopped here. And you continually increase the applied stress, you got more and more GNDs piled up, but this dislocation can never get across, which means the matrix will not deform plastically, while this one becomes stronger and stronger. Effectively, when this one starts to deform, the matrix is also plastically deforming. Then that makes this softer grain almost as strong as the matrix. That's why the total strength does not come down. Okay, here's how you explain this phenomena at the dislocation level instead of the abstract ideal stress strengthening. Okay, then where is the ideal strain hardening from? During the plastic deformation, you have ideal stress hardening. Okay, look at this sample. This is a tensile sample. It deformed by with a global strain of 9.4%. Okay, These grains, like these recrystallized grains, before tensor testing, they are all equiacid, which means they are all recrystallized grains. They are equiacid. And after tensor testing for 9.4%, you see they are all elongated. And by their length of the thickness ratio, we can estimate their strain. Their strain is about 45%. Okay. Okay. The larger grains are deformed by 45%. The overall total strain is global strain 9.4%. We can assume that this matrix deformed much less than 9.4%. Okay. However, the strain needs to be continuous across the boundary between the larger grains and the smaller grains, which means near the boundary, it needs to have strain gradient. As we discussed earlier, the strain gradient needed to be accommodated by GNDs. Okay, so if you have GNDs, you produce back stress. If you have back stress, you produce forward stress. If you have back stress and forward stress, you produce IGDS stress. Then that's why you have IGDS strain hardening here. The IGDS stress can be measured by unloading, loading test using this equation. This equation recently divided by us, derived by us. If you have more interest, you can come to this paper. Before this, people try to calculate back stress. They believe it as back stress using this equation. This equation is not that good because first, it's not derived mathematically. Secondly, it will give you a lot of scatter in your measurement of the back stress. Okay. How do you measure this IGDS stress? And in the literature, see here is an unloading curve. This is the reloading curve. Okay. First, we need to determine what's the sigma U. This is the unloading yield stress. Sigma R is the reloading yield stress. Okay. During the unloading, you have a linear segment of this unloading curve. Okay. When it deviates from this linear part, you have to decide how much does it deviate before you decide that's the yielding point. So this is a conventional way to use this. I find that is problematic. And the best way is to define it by how much this slope is reduced. This is a more accurate way to do it and easier way. You can say 10% slope reduction or 20 or 5% or 15%. No matter how you do it, say if this use 10%, then you have to mark this is measured by 10% slope reduction. What is great about this equation is when you use a different percentage for this unloading and reloading curve, this sigma U, one decrease, the other increases, their variation cancel each other. So give you very stable data you can measure. Okay. Okay. Then last time remember we showed you that hydrostructured laminar titanium give you this really great property, and this is why. If you look at the measured IGDS stress, this is the IGDS strengthening from here. So IGDS strengthening is about 350 megapascal, which means the hydrostructure, due to hydrostructure, they increase this yielding strength by 300. I'm sorry, by the IGDS stress at the yielding is about 400 megapascal, which means they increased the yielding strength by 400 megapascal. Then the yield stress, the IGDS stress continue to increase with applied strain. That means you have continuous IGDI work hardening. Okay. Another example is a gradient structure that I have steel. Okay. For uniform, of course, I have steel is a steel developed for the auto industry. And of course, you want them to be strong and tough. This is basically for making the body of the cars. Okay. And to make the IF steel stronger, people try many different ways. One way is to decrease the grain size, make it ultra-fine grain. See, as the grain size decreases, you see the ductility, the uniform elongation will decrease. However, above 400 megapascal, you can see the ductility decreases to like 3%, which makes it useless. You cannot use it anymore. Typically need like over 10%. You can to be safe. But if we make this gradient HF steel, we can say this is out of the traditional line here. And what's more is when the strength is 600 megapascal, the ductility is still 10%, which means you can increase the strength of the average steel plate by 50% and make it still okay to be used in the cars. You increase the strength by 50%, then you can reduce the weight of the car, make it more fuel efficient. That's important for new energy cars like electric cars. Earlier, we also said heterostructured materials need to have a 1+1 rather than 2 synergy. Okay, here you can find this one for the gradient IF steel. Okay, so this is the strength, yield strength of coarse grain IF steel in the center of the plate. This is the strength of the surface layer, nanostructured layer plus ultrafine grain layer. We'll call that a gradient layer. The strength is about 400 megapascal. Okay. Then we vary the volume fraction of these two. If there's no synergistic effect by the rule of mixtures, it should follow this linear line. This is a blue line. However, what we actually measured when you vary the volume fraction, they follow this red line. So above rule of mixture. So this is so-called 1+1 larger than 2. This actual strengthening is caused by the heterostructure effect, which is IEDS strengthening. In addition to HDS strengthening, there's another factor which gives heterostructured materials better property, as the change of stress state. Okay, now here's like a gradient structured material. There's a surface gradient layer, the soft central layer. Okay, sandwiched between two high strength gradient layers. Okay, you can imagine, let's see, do a virtual tensor test under tensor stress, okay, at a linear stage. So both of them are deformed together like this. This is like under, you have uniaxial applied stress, uniaxial load, okay? However, when the stress increases to a certain level, the softer core will start to deform plastically. Okay, when it deforms plastically, to maintain the same constant volume, the softer core will shrink faster in a side way, because we know in a tunnel test elastic state, there's a when you make this elongation, this sample will shrink sideways because of the Poisson's effect. How about you shrink? It depends on the Poisson's ratio. For most material, the Poisson's ratio is 0.3, which means if you elongate 1%, the side will shrink by 0.3%. Okay. However, for plastic deformation, if we elongate 1%, the side will shrink by 0.5%, which means the center will shrink faster than the surface layer. And that causes a bigger problem because initially you apply a uniaxial stress. Now you have a two-dimensional stress as a result because the center cannot shrink freely. It's constrained by the surface layer. On the other hand, if the surface nanostructure layer also started to plastic deform, we know the surface layer has a low strain hardening rate. It's not stable plastically. It will start necking first. Then that's when the surface layer will shrink faster than the center layer. Center layer become more stable. As a result, the surface will shrink more. And this is just our hypothesis in the beginning. Then later we did a measurement of one of the samples of the testing. We measured the side, see the height profile. Is the height profile. Okay, which means near the surface, near the width of this, the surface layer is shrinking more. It's lower in the center. So this verifies that, yes, this indeed, they shrink differently. They converted this 2D stress into 1D applied stress into 2D stress, two-dimensional stress. Imagine if the other heterostructure, if the soft zone is totally embedded into the hard matrix, it will develop 3D complex structure, developing the 3D complex stress. Okay, so this complex stress, it may activate multiple slip systems to promote dislocation interaction. Okay, dislocations from different slip systems. They may cut each other, interact with each other, and entangle with each other, and make a dislocation accumulation more effective. That will improve the strain hardening. In addition, it may promote the accumulation of statistical and GND and GNDs. Okay, the GNDs maybe got entangled up, increase the GND level, so further increase the IGDS stress. What I'm seeing here is this complex stress stage. When you deform heterostructured materials, it may produce complex stress stage internally, will give you better property. And here's an example to tell you that the complex stress state indeed give you better mechanical property. To prove this concept, here are two samples. This is basically both of them are gradient structure samples. The difference is one sample has both two gradient layers, two surfaces, both of them are gradient. The other sample has only one side of the gradient. The other side got polished off. Basically, initially you process the sample with nanostructured surface and the gradient layer on both sides of them. Then some of the samples, they just polish one side off. With everything else the same. Now you can imagine when you deform this, there's a soft layer and the hard layer, they deform differently, they constrain each other, they develop different stress state. And this with 2 layers and 1 layer, 2 surface layer and 1 surface layer, they develop different stress state also because this here the constraint is less. And indeed, here, if you look at this stress strain curve, this is a consequent core, the stress strain behavior is like this black curve. The hard surface layer, gradient layer, has higher strength like this. But if you look at this green line, this is 2 layers, the double layer. Okay, this number, the 12% means 12% of the surface layer. Okay, gradient layer is 12% by volume. The single layer, double layer. The volume fraction of the layer is the same, but you look at the strength. This yield strength is much higher. And then you look at the ductility. The ductility is also much higher, which means there's a different, this verifies that the different stress state indeed give you much better mechanical property. So let me summarize. So for heterostructured materials, there are 2 factors to give you superior property. One is that IGDI stress, IGDI strengthening, IGDI hardening. Other is this complex stress state during the deformation, which further increases the IGDI effect. And actually can also consider the complex state. The stress state is also part of this IGDI effect. Okay, the complex stress state really give you better property. So these are 2 big factors. If you compare dislocation hardening to IGDI hardening, in a conventionally we only know dislocation hardening. Now how do you compare them? So for dislocation hardening, this is well studied. Using the Taylor equation, you know what that is. It is typically isotropic, it's non-directional. Okay, there is a shorter range interaction, dislocation interactions, because when one dislocation cut in tangle or cut with another dislocation, it gives you dislocation hardening. So which is why it's related to total dislocation density. On the other hand, for IGDI hardening, it's not well studied, which is good for us researchers. It is a long-range internal stress caused by long-range internal stress. It's a kinematic. Okay, this is directional. This stress is opposite to the applied stress. It's related to pair of GNDs only. It's also correlated with the Bossinger effect. Okay, heterostructured effect. Again, the Bossinger effect has the same physical origin with are GND pair up. So you can imagine heterostructured materials also have high Bossinger effect. Then you say, okay, heterostructured materials are great, that's so good. I also want to work on that. How do I design new heterostructures or new heterostructured materials? Let's consider what give us this IGDI stress. It's caused by GND pile up against zone boundaries or interfaces. Because of that, you'd like to have high interface, zone boundary densities. Okay, then with that concept, you can design the geometry of this soft zone and the size of the soft zone, as well as the distribution of soft zones. So that's why it's not just if you got a good IGDI effect, this is how you need to do it. You need to design the density, the size and the shape of the zones. Okay. But you also need to have appropriate interface spacing. What I mean is if we have interface too small, like get to nano size, then you have no space or dislocation to pair up anymore. So which means that it will not be effective. So you have an optimum space interfacial spacing. Okay. Of course, the space is too large, then it's not effective. Thirdly, if you have a if you fully constrain the soft zone, which means the soft zone embedded in hard matrix, give you best property. It give you best actually yield strength. This is simple to understand because if you have a soft zone embedded in hard matrix, the soft zone cannot be plastic deformed until the hard zone become plastic deformation. So the constraint is very effective. On the other hand, if the hard matrix is embedded in the softer zone, the softer zone can start to flow first. It can flow around hard matrix. The hard matrix cannot, which means soft zone cannot effectively constrain the hard matrix, which is not good. So remember, to have greater property, you have the soft zone embedded in the matrix. This is totally opposite to our conventional idea of designing metallic materials. In conventional materials like this steel, it is not strong enough. Then you want to add hard second phase into it. The hard second phase is always the minority. We call that using the hard second phase to reinforce softer matrix. Here the concept is totally different. Here we call that the hard matrix is not ductile enough. We are using softer zone to make the hard matrix more ductile. So softer zone are minority. Typically, from our experience, the volume fraction of softer zone should be in a range between 20 and 30%. That makes it the most effective. Of course, the optimum volume fraction could be affected by the strength difference between the two different zones and other factors. Those we do not know, we do not understand well. So that may take years for us to understand, which is a good thing because we can justify our research funding. Earlier, in here we say this must have appropriate interfacial spacing. Okay, here is some evidence. Here in this layered structure, which the copper bronze layer, and here you can see as the interlayer thickness decreases, which means the interfacial distance spacing decreases. As the interfacial spacing decreases, initially, both the yield strength, ultimate strength, and the ductility increases. Okay. Yes. And however, I will show you later, when this layer thickness becomes very thin, the strength will continue to increase, but ductility will start to decrease because this is optimum interfacial spacing. Okay, before we go to optimum interfacial spacing, I need to introduce another concept, which is called H bar. H bar is heteroboundary affected region. Okay. Earlier we said that the GNDs will pair up against the zone boundary. If you look at this cartoon, you can see the GNDs distributed in not uniform. Near the boundary, you have higher density. Okay. Then we measured the GND density as a function of distance from the boundary in this sample. And we found, yes, you see, indeed, there is a non-uniform distribution. There's a density gradient. See, this gradient, there's a thickness, boundary thickness within which this density gradient is here. We call that heterozone boundary affected region, because this is the region affected by the boundary. Okay. You can also, like, with increased strain level, the GD density become higher and higher, which means the HDR stress will be higher and higher, and that's what gives you HDR hardening. This zone, this affected region, the width is typically a few micrometers, like below 10 micrometers, certainly, like from 2 to 10 micrometers. Okay. Another way, if you look at that cartoon, another way is we talked about the strain gradient. So we also measured, there's also a strain gradient. This can be also measured. Here, this measurement is by high resolution digital correlation, image correlation. Okay, indeed, there's a strain peak near the interface. However, here this gradient, this strain gradient is negative. Okay, the cost is negative. So this width, so this peak, this width is also the same the H bar. Okay, this width H bar, hetero boundary affected region. This H bar is the same H bar here. So this experiment verifies that our concept is correct. So most of these HDR stress are produced due to the GND accumulation in the H bar. Okay, so which means you want this hetero H bar area, the volume fraction of the H bar become the highest, the higher the better, because that's give you the highest HDR stress. And that's indeed what happened in this sample. Okay, here you can see as the interfacial spacing becomes smaller and smaller. Initially, the 150 micrometer. Initially, when it becomes smaller and smaller, both uniform elongation, ductility, and the yield strength, initially both increases. Okay. However, when it reaches the optimum thickness, about 15 micrometer, you have the best strength and ductility combination. If you further decrease the thickness, like the 7.5, 3.7 micrometers, the strength will continue to decrease. Strength continue to increase, but the ductility started to decrease. That's that we compare here. It started to decrease, which means, indeed, there's the optimum interfacial boundary interfacial distance, will give you the best heterostructure effect, or highest HDR strengthening effect. Okay, so when you design the heterostructures, you have to consider this also. Okay, there are all different ways for the dislocations GNDs to interact with the interface. Those are several things we can think of. Some are verified, some are not, and we want to study this, and that would be great. The first is all the GNDs got paired up in front of the zone boundary. This is the ideal case. In our textbook, everybody knows the dislocation all got paired up in the blocked here. Another scenario is all the dislocations got piled up. However, the dislocation at the front are pushed into the boundary. Then it got some clamp and stayed in the boundary. So you can put more into it. So this type has also been verified by in-situ TEM. And the third type is all the GND the piled up against it, but at the boundary it pushed across it into the hard zone. One example is if this is not a zone boundary, it's a green boundary, you can push them through. Okay, this will leave a residual dislocation at the boundary. So this theoretically can happen also. And another type is the dislocating got piled up here, and then get reflected off like a mirror. This can also happen. This has been observed actually, but it's not published yet. Okay, see, all this may affect the production of HDI stress, the production of back stress, forward stress, and HDI stress. So there, you can see there are so many fundamental things we do not know yet in this new field. So much new science waiting for us to explore. Earlier in this I said that this has been verified, and here is the experimental verification. And this is by Professor Hao Zhou, who did the in-situ TEM to see how the dislocations are interacting with the interface. And here observed the front radial source. You see this front radial source emitted many GNDs. The GND will come to the interface, and what he found is the GND that come here and then all mostly disappeared at the interface. Okay, if you look at the video, it'll be there. We don't have time to give the video. Another important thing he found is for each GND interface, it will, for each front radial source, it will emit some dislocations, then disappear and deactivate. Then in some other places, and a new front radial source will get activated, and then emit new dislocations and get deactivated again. So this one disappeared again. So this means what? This means front radial source in the metal is dynamically generated and dynamically destroyed. Okay, this is what we do not know in the textbook. We did not know earlier. This is a dynamic process. Then you may wonder how this is dynamic. How does that happen? And there, if you are more interested, I suggest you go read this paper. Okay, there's too much to put that into this tutorial. So to summarize, this in-situ TEM tells you that front radial source still exist, still in a green interior, and it's not from the zone boundary. And so this clarified a long-term argument about the dislocation sources. There are some people saying, oh, all the dislocations are from green boundaries. They're not from a green interior. And here we show that that's not true. But we're not saying that the green boundary cannot emit dislocation. We simply do not know. And it may be possible, but here it's not the case. Here the front radial sources are dynamically formed and destroyed. This is something new we do not know. There's a density gradient for front radial source. Higher density near the interface. It means if you get closer to the interface, you get a higher dislocation front radial source, which is why it gives you that negative strain gradient. So next strain gradient is not caused by grain boundary disagreeing emission, not caused by front radius source, it's caused by front radius source density gradient there. Because the dislocations GNDs are resolved by the grain boundary, it also tells you that you cannot quantitatively relate GND gradient with the strain gradient. Okay, this will complicate the gradient plasticity theory, because in the theory, there's a modeling, they always assume one-to-one correlation. Now it tells us that it may not be true. At least in this case, it's not true. In other cases, I'm not sure. I assume that is the ideal case, which may not be true in most materials. This also tells us if you do TM observation after tensor test, you will not be able to find this new science. So you have to do an in situ test. Post-mortem TM test is not enough. Here I'd like to show you another prominent feature deformation mechanism of heterostructures, which is local strain band formation. Here we can show you 3 examples. This is a laminated structure, layered structure. Basically, you have the copper layer, bronze layer, copper layer. You see all those strain bands formation. And then you can look at another one is a gradient structure. You also see this strain band formation. And this one is a bimodal structured copper. It also gives you this strain band formation. By the way, if you get a uniform metal, a same metal is uniform, it does not form this or does not form this match, which tells us that local strain band formation is a unique deformation mechanism for heterostructured materials. Okay, and this local strain bands formation, especially when these strain bands they have high density, they are dispersed uniformly. This can prevent local localization of large strain localization to fill your sample. Okay, we still are not sure how these local strain bands is related with the GND pile up and other things. So we have a lot unknown science here for us to study, which is a good thing, again, for researchers like us. Okay, for students also, which means after your PhD graduation, you still have a lot of science to study in this new field. After all this, I think now you may have already understanding about heterostructured materials, and it has a superior property and everything. You think, wow, this is a good area to study. Here I'm going to tell you that the biggest advantage of heterostructured material is what? Is that they can be processed with the current industrial facilities at a low cost. Okay, if you check the literature for the last several decades, and there are so many new materials out there, spent like billions of taxpayer dollars money, and then you ask how much of those, how many of them are being commercialized as benefited the society. I'm sorry to say that not many, because of 2 big issues. One is, can you produce it in large industrial scale? or if you can, how much it cost. If it costs too much is a problem. However, for heterostructured materials, we can produce them easy at low cost. Like a heterostructured steel, and using the current hot rolling, cold rolling, you can produce them at the same cost as the conventional steel, but give you much better property, which means it's very easy for commercialization. Okay. Then there are so much science which is not understood, many fundamental issues to be studied, to be clarified. They will justify our research for the next 10 to 20 years. So welcome everyone to join this new field. Lastly, I'd like to say heterostructured material concept also applies to functional materials. Just like a nanostructured metals and nanostructured functional materials. Here's one example. The heterostructured magnetic material that breaks the trade-off between magnetization and coercivity here. This is by Professor Xiangyi Zhang at Yanjing University. So he has a mixture of hard magnet and soft magnet, and this is what we got outside of this trade-off. Okay, and for structural material, the superior property is by GMD coupling at the interface, GMD interaction with the interface. Here for magnetic material, this is superior magnetic property is caused by the magnetic coupling. I guess everybody knows magnetic coupling. And if you understand magnetic coupling, then that can help you to design heterostructured magnets. And there are some other functional materials exhibit a similar effect. I'm not going to deliberate here. And this heterostructured materials field is developing very fast. And despite the COVID pandemic, and here are the many international conferences here. The first one is the current one, which is the first international conference at heterostructured materials, which will open starting very soon. And the second one, Chinese Material Conference, there's always a symposium there. However, it was canceled this year and last year. And also at the TMS meeting in the US, there's this UFG and H, which means heterostructured, is a biannual conference. So the next one is in this year, I think it has one already. Next one will be in 2024. There's another biannual symposium, heterogeneous and gradient materials. And next one will be 2023. I'd also say that, there's a nano SPD international conference due to COVID pandemic. It was canceled last year. New one will be scheduled for the next March. There will be a session on this also. Okay. With that, I thank you for your attention. If you want more information, got some papers to read. Here's the website. When you go there, you can download papers there. All the papers there are those I believe will help you understand this new field. Thank you. I will stop here.